Dr. Cooper is the chair of pediatrics as well as the director of the Institute for Clinical Translational Science at UCI, and he was one of the leaders that was able to make UCI competitive for the grant that they received to build ICTS. So, Dr. Cooper, welcome. Good to have you.
Thanks. Okay, well, thank you very much. Thanks,
Absolutely.
Shahram. And you guys are lucky to have Dr. Lotipour and Professor Vaughn, Jessica Vaughn, who've done such a wonderful job in putting this course together. And Dele, of course,
yes,
who's part of the Institute for Clinical Translational Science, which I'll talk to you about, and has a great deal of relevance to everything that you're doing, and is the leader not only of the program in public health, which will become a school, we hope, soon, and is also the leader of the training component of this new entity that we call the Institute of Clinical Translational Science. So, in my, you give me a 4-hour
yes,
lecture?
4 hours.
So,
yeah.
if anybody's awake at the end of the day, I'm going to use that one.
Yes.
I'll try to get out in front of you a little bit. So what I thought I'd talk about is an example from my own recollection, things that occurred in my career, starting before I went to medical school, but some of the things happened while I was in medical school. And I think to talk about translational medicine or research is very abstract. So I'm going to talk about a real event, a real discovery that actually profoundly changed not only how we care for babies, but actually how we care for adults as well. And so I call it this talk, The Grunt Herd Round the World, or how pediatrics, and as a pediatrician I have to give us some credit, revolutionized critical care. And this was in the 1960s, and in many ways reinvented translational research. So let's go back a little bit to this guy named Abraham Flexner. Does anybody know who he was? So it's actually pretty important for all of us in medicine in general. In the 1900s, there were about 200 or 300 medical schools in the United States. And many of them were, it's not like today, medical schools were not highly regulated. And a lot of people were getting degrees, and it was dubious what they were learning in these schools. There was a lot of snake oil and herbal remedies that no one had ever even tried or considered to do in a laboratory. And the Carnegie Foundation hired this guy to go and survey all of the medical schools in the United States. And it ended up by closing about 2/3 of the medical schools because he very much believed that medical schools needed to be tied to what we now call evidence-based medicine, which of course is really nothing new for rigorous scientific proof that if I give a medicine to another human being, I ought to have some reason to think that it actually works. And as you heard about this talk just before about cholera, you can see that medicine in and of itself doesn't work, that there are all kinds of environmental, social, cultural conditions which contribute to this. But because of Abe Flexner, we entered into this modern period of medicine. And what Flexner realized was that a modern medical school, you have to have scientists literally next door to clinicians. That you can't separate these two people. The practitioners, in order to be successful, should be speaking with the researchers so that the basic science discoveries get translated as quickly as possible to actually helping people. Now, we have not solved this problem. This still is a big problem. You guys are here at UC Irvine, you see all these beautiful labs, and a lot of people are studying biological problems or problems in physics or math or informatics or statistics that we think could be relevant to actually improving human health, but how do we make this link? And the idea that Flexner introduced was that medical education needs to be this big yeasty group of multidisciplinary scientists and practitioners, and it's only through communication among all of these people that we can really make progress. And this very much, I think, fits with the mantra of the UCI School of Medicine, which has these 3 themes of discover, teach, and heal. and that these are really linked together. And I think those of you who go into any kind of a health profession, no matter what it is, this is why American medicine, I think, has made such progress, is because we understand that these three themes are really very, very much related. So let's talk about this disease that sort of got me interested in this whole thing. So this is a disease that's called respiratory distress syndrome. And these are chest x-rays from newborn babies. You could probably figure out that those are not adult films. And I think as you look at these, you really don't have to have a lot of training to see that there is a really big difference between these two x-rays, right? Like, what do you see? What's different about these two x-rays? Speak up. There's no wrong answers. Only Dele can give a wrong answer, so I won't even call on him. Obvious things. What's different about those two x-rays?
The RDS x-rays, well, the ribs are kind of like elongated.
Looks like maybe there's a little bit different in the shape of the ribs. What else? What about this area? What is that? Why is that darker over there? Does anybody know enough about x-rays to know why that's darker? Something that's dark in an x-ray, does that mean there is tissue or there's no tissue? There's no tissue, right? So this is air. These are the lungs, right? So what can you say about the sort of the darkness of these, the x-ray here and the x-ray here?
They're significantly less than the RDS.
You. Weren't you in
Yeah.
Go ahead, speak up, sorry.
Oh, I was going to say the same thing. There's more RDS.
Yeah, there seems to be, instead of this normal x-ray, how many of you knew this was normal? No, just joking. In the normal x-ray, that's exactly what you should see. Really well aerated lung. But in this one, it's not so well aerated. Look at this, for example. Here's the border of the heart in the normal x-ray. You can barely make out the border of the heart over there. So it suggests that there's something in the airspace of the lung that shouldn't be there. So if you were to take a guess, which one of these babies is having trouble breathing? The RDS baby, right, because the lung's not functioning normally. So this condition, called respiratory distress syndrome, was something that we saw in many babies that were born prematurely. So if you had a premature baby, the baby might, despite the fact that it was premature, the baby might survive for a while, and then the baby would develop a great deal of difficulty in breathing, okay? And when we started to look at the lungs of these babies, we found that they got full of this fluid, and I'll show you some pictures at the cellular level, and they were in respiratory distress. These babies were gasping for breath. Many of them died. They became hypoxic. And so the name respiratory distress syndrome, or respiratory distress syndrome of the newborn, was what this particular disease associated with prematurity was called. And this is what it looks like at the cellular level. So in the normal lung, you see these little sacs, and these are called the alveoli. These are these little balloons in the lung where you have this incredibly thin membrane, and you have blood vessels in here, and this is where gas exchange takes place. Remember, you've got the carbon dioxide that's produced by metabolism comes back to the lung, and it exchanges for what gas? Oxygen. So you've got this very, very thin membrane, these balloons that fill up with air, and it facilitates this incredibly elegant mechanism through which we all breathe, get rid of the CO2, and load new oxygen onto the blood. So this is the normal lung, but look at this lung. This is a lung from a baby with RDS. It was also called hyaline membrane disease. Hyaline is, I think it's either a Greek or Latin word that means glass-like. And when you looked at the autopsies of these babies, it's almost as if their lungs had this glass-like membrane that was sitting in between where normal gas exchange should take place. And you can see in the microscopic view, instead of these nice, big, empty alveoli, they're full of inflammatory cells and cellular debris. And so you can see pretty quickly that this baby's going to have a hard time breathing. So this at least was the cellular mechanism of this disease that was called hyaline membrane disease. Well, let's look at the mortality of this disease. In moderate to severe RDS, until the years about the late 1960s and early 1970s, This was about 50% fatal. So if a baby were born prematurely, survived the first couple of hours, it then went on to develop this RDS, and in severe cases would almost inevitably die. Something happened here. You can see there was some discovery or set of discoveries where the mortality of this disease plummeted. There was a discovery, there was a translational moment, and that's what we're going to talk about. By the way, I'd like to show this. So the funding, the governmental support and funding actually went up at this point, and I'm going to explain to you why, because it's a very interesting point of history and the interaction of how history and science and all this stuff come together. So 1960s, who's this? Right, that's President Kennedy, and there's Caroline and John. For those of us who remember, I guess that's me, huh? This was, he was this, phenomenally charismatic young president, and he had these young children, and the idea that you had the White House instead of a bunch of old stodgy guys, you had kids running around. Was a very exciting time. Now, the Kennedys had a singular tragedy while they were president, besides the fact that he was assassinated. It was an interesting time. Sputnik, first satellite. I remember I was 9 years old or something. But this was a big deal when the Russians put Sputnik into outer space, and you'd have all these kids out in their backyards, and they would see something, and they would go, "That's it." But I don't know. We were all looking for Sputnik in those days. And then the U.S. was sort of getting going, and all these, the initial part of the space program, all these U.S. Rocket ships were blowing up. It was a little bit disappointing. The war in Vietnam was going on. Okay, so what happened was early, well, actually 1963, Jackie Kennedy had a premature baby. The baby was only about 4 or 5 weeks premature. And the child died just 39 hours after his birth. And he died from respiratory distress syndrome. So you can imagine this was a huge tragedy. Everybody had followed this pregnancy, how exciting it was. President of the United States had a new baby, and the baby dies. The obituary of this child pointed out that at that time, all that could be done for the victim of hyaline membrane disease is to monitor the infant's blood chemistry and to try to keep it near normal levels. Thus, the battle for the Kennedy baby was lost only because medical science had not yet advanced far enough to accomplish as quickly as necessary what the body can do by itself in its own time. Pretty dramatic statement. So what did we know about this hyaline membrane disease at the time that the Kennedy baby was born? This was from 1965, from one of the then state-of-the-art textbook, Schaefer and Avery Diseases of the Newborn. Hyaline membrane would appear to result from an excessive outpouring of fluid from the terminal respiratory segments, either transudate from congested, perhaps damaged capillaries. Just what is responsible is not known. So we didn't know why this was happening at all. They went on to say in this textbook, cyanosis is seldom noted until later. When dyspnea becomes severe, dyspnea, difficulty breathing, the disease progresses quickly in some infants so that they become seriously ill. Thereafter, the infants gradually improve, or, as in the case of the Kennedy baby, respirations become weak and irregular, the color becomes ashen gray, and they die. Pretty dramatic reading for dry medical language. 3 principles of treatment in 1965 have been universally accepted. These are the use of oxygen, high humidity, and antimicrobial drugs. We would always treat with antimicrobial drugs, even if we didn't know what we were treating. So this is where this story gets really, really interesting. When you would look at these babies, and I went to medical school at UC San Francisco between 1970 and 1974. And there was a lot of work being done there in this disease because when the Kennedy baby died, the federal government, it seems to be connected, started putting a lot of money into research into RDS, into hyaline membrane disease and so forth and so on. And at UC San Francisco, they created what was called the CVRI, or the Cardiovascular Research Institute. And it collected from all over the world some of the greatest scientists in the field of lung disease and in hyaline membrane disease in particular. And the people that were sort of teaching me as a medical student were the people that were working on this problem. Now, there was a really interesting observation about babies with hyaline membrane disease, and I actually remember seeing a baby with this, and that is that these babies had this really unusual breathing pattern. They would grunt. So you would watch this baby that had HMD, and you'd look at it, and it would go like this. It would make this grunting noise, just like that. So, most people were kind of like, okay, they grunt. But a few people said, what's going on there? Why are these babies grunting? Why are they making this noise? There's got to be some reason that they're making this noise. What is it? So this was an article that was written, I think this was in 1968, and it talked about the significance of grunting. So one of the elements of any kind of translational research or science in general is what I call keep your eyes open at all times. Whatever's happening around you, pay attention to it. When you are studying cholera in India or depression among undergraduates at UCI or any of the things that happen, don't just accept everything that you've been taught. Keep your eyes open, make observations, really think about it. And it was surprising that there had never been an article about this because the grunting part of this disease is very, very salient. When you saw this baby, this was a loud noise, and you go, why is it making this funny noise? So they actually went to try to study the physiology of what this grunting was about. Now, this is a little complicated. The first thing is, so what they're doing is they're measuring pressure within the lung. So they actually put tubes down, transducers, and they measured pressure. So this is reverse, this is negative pressure. So imagine you're trying to breathe, and you've got this lung, and here's the atmosphere. The atmosphere pressure is what, by definition? 0, right? We call it 0. It's not truly 0, but we call it 0. So to move air from here to here, what has to happen to my pressure in my lung? It has to become negative, right? Otherwise, you won't move the air. So keep that in mind. And this is more negative, and this is positive. This is super above atmospheric pressure. So you'll notice that in the normal baby's breathing, when it breathes in, it develops a more negative pressure. Air moves in. And then as the baby breathes out, it approaches atmospheric. Okay? But in the baby with RDS, look at what happened during the grunt. During the grunt, the pressure in the baby's lung was above atmospheric. So that what the grunt was doing is that the vocal cords were closing off, and the baby had to push that air out against an obstruction. Is that clear to everybody? Okay, well, what was the physiological consequence of this? So we've got these lungs that, as we showed you in the picture before, were not operating well, right? They were full of junk. They were not these beautiful, fluffy, wide-open lungs. If I were trying to keep my lungs more open, what might I do? I might pressurize them, right? I might try to put some pressure in there to keep them open for as long as I possibly could. And so when these curves were looked at and people started to think about it, they realized this is what the baby was trying to do. The baby had a lung which was closing off like this. And I'll tell you why it was closing off in a second. But instead of those beautiful little alveoli staying full of air, it was collapsing. And in an effort to keep as much gas within the lung as possible, the baby was trying to do what it could to keep that lung open. Now remember, at some point, it had to get air from the atmosphere into the lung. So you'd have to create a negative intrathoracic pressure, right? Otherwise, you couldn't move the lung. So, in fact, that happens here. And then the lung would collapse again. So the baby could never really achieve a state where the lung was always inflated. But it tried. And that's what the grunt was all about. And in many babies, that grunting, if the baby could get through a certain maturational stage, that would save the baby. Okay, so what happened? So when this became clear to people that what was going on was that the baby was trying to keep its lungs in positive, greater than atmospheric pressure all the time, people started doing some funny experiments. When you would take a baby like this and intubate it, and you could intubate a little baby in those days, namely you could put a tube into the baby's airway, did the babies get better or worse? The babies actually got worse. Because what could the baby not do when you put a tube through its trachea? It couldn't do the grunt anymore. So what happened was, and you read about this in this previous article, is that the babies would get worse. They would become more cyanotic. Their oxygenation would drop. So somebody had this clever idea of a very, very simple thing. So you have the endotracheal tube in the baby. It's going to the lung. And they said, how do we pressurize this? How do we keep the baby's lung always greater than atmospheric pressure? And it was very simple. And I think it was a nurse who discovered it. They took, from one end of the trachea, they took a tube and they put it in a column of water. What happens when you take a tube like that that's connected and you put it in water? What's the pressure in that tube? It's the number of centimeters of water there, right? And all of a sudden, dramatically, these babies could breathe. Simply because you pressurize the lung. You open the lung up. And this article, which appeared in 1971, George Gregory this was all from UC San Francisco. This guy was one of my instructors. This guy's still alive. Phibbs is still alive. And they were doing all this research there, wrote an article in the New England Journal of Medicine, and they invented a mechanism to supply positive airway pressure throughout the respiratory cycle, and they called it CPAP, or continuous positive airway pressure. So they kept the baby's lungs pressurized throughout the whole respiratory cycle. Of course, they varied it, right? When they wanted to fill the lung up, a little more pressure. When they wanted to let the baby breathe out, they lowered the pressure. But the baby's pressure, the pressure inside the baby's lung, never went to below atmospheric. The lung never collapsed. And here's what they found. They wrote this article in 1971. Here's some of their data. So here is PaO2. This is the amount of oxygen in the blood. Normal is about 90, okay? And they had a bunch of these babies with respiratory distress syndrome. And here's the amount, the millimeters of mercury of continuous positive airway pressure here. And this was in a series of, I think it was 15 or 20 babies. And look at this really remarkable relationship. As you apply the CPAP, you can oxygenate these babies. They turned nice and pink. You save them. So Dr. George Gregory was one of the pioneering clinician scientists in the battle against RDS. Recently, this was a couple of years ago, wrote an article about the history of this. And he identified some of the key components that enabled this particular success. He noted, looking back, one wonders why others did not develop CPAP earlier. All of the clues were there, and in hindsight, they were obvious. I mean, if someone 10 years before had said, gee, why is the baby grunting? Maybe we can do something about that. There was really nothing fancy about taking the end of an endotracheal tube and putting it underwater. This was not high-tech in any way. And this is a theme that resonates with current calls to break down the barriers that impede the rapid transformation of basic knowledge to clinical practice. So this is something that we here at UCI and in many other places have tried to pay a lot of attention to. I just want to make one more point and then we'll go on with this. What was it lacking? Why did the premature baby's lungs collapse? What did that baby's lung not have? Does anybody know by any chance? Surfactant. And so what happens in the last trimester of pregnancy as the lung develops is that the lung produces a substance that's called surfactant, which is actually a soap. And you all know what a bubble bath is, right? You pour that, before you pour the bubble bath in, you get a little bit of suds, right? You get a little bit of bubbles. But bubbles, unless they're in a particular chemical composition, bubbles are not stable because they rapidly get smaller and then they burst. But when you put the soap in, when you do the bubble bath, what happens? You get this stable bubbles, right? And you take your bubble bath. So there's something about this soap that permits these bubbles to stay open. And that's exactly what was happening in the lung. You had these millions of bubbles, as it were, because of the alveoli. And when you coated the walls of the surfaces of those alveoli with surfactant, which is bubble bath, sort of, not so far, they remain stable. And that's what surfactant was. And during that period of time, in the 1970s, Tooley, who was one of the articles there, invented this test where if you got a little bit of the amniotic fluid from the mom, who was like maybe threatening to have early delivery, you could actually shake it up and you could determine whether or not the baby had been producing surfactant, so that you could know in advance whether that particular baby had matured enough that it was about to produce enough surfactant to survive premature delivery. So CPAP was a huge step forward. The next step that took place was the development of artificial surfactant. And artificial surfactant, I had the great privilege of working with Alan Jobe when I was at Harbor UCLA. He was one of the pioneer researchers in this, and now it is standard of care that babies born prematurely will always have some kind of a CPAP, some kind of a continuous positive airway pressure, and they always get a squirt into their lungs some of this artificial surfactant. And so at that time, in the 1970s, you maybe could save a baby that was 25 or 26 weeks. Maybe. Now, a 25 or 26 week pregnancy baby is very likely to survive and very likely to survive without a lot of complications. We can save 20-week pregnancies right now because of these methodologies. So it has really been a remarkable set of progress that took place, and it started with this fairly simple understanding of what the baby was doing when it grunted. So Gregory said, what were the things that had happened at the CVRI that led to their ability to figure this out when nobody else had been able to? So he talks about the infrastructure, and it facilitated innovative, frequent, and effective observation of the clinical interaction, whether it was in the hospital, clinic, or community. And I'm sure the group that did their studies, that you did your report on cholera, there's so much of our understanding of cholera or smallpox. Eradication of smallpox is another great story. I don't know if you guys have studied that, but you know, there is no smallpox anymore in the world. And if you guys want to read a great story, a page turner, read about the eradication of smallpox and how that occurred. And smallpox, I mean, cholera is a terrible disease, but it's, you know, if you give oral rehydration or you even rehydrate the baby will live, or the adult will live, whereas smallpox is a disfiguring, terrible disease that left many people dead. Smallpox has been eradicated, That's a great discovery. And a lot of the ability to do this was based on keeping your eyes open. You had to look at the cultural, social, bacteriological, physiological interactions that were going on in the communities. Gregory also talked about the need to create multidisciplinary teams, physicians, nurses, basic scientists, community partners, the participants and the patients themselves. We often forget about that, among whom information is shared openly and frequently. And finally, I thought that Gregory said something that was very, very compelling. And what they had at the CVRI was an inquisitive environment where everything was questioned and there was no status quo. It's kind of hard to achieve that because I know that everybody's worried about things like grades and getting into this school and that school and the other thing. And to be really independent is sometimes hard because you're worried about not towing the line or not doing things in a way that might get you that good grade. And you know, it is a problem, but I'll tell you, if you look at all the really remarkable discoveries, they come from folks who were willing to be a little bit independent at time and to think of things in a new way. Here was interesting. This is George Gregory. He was one of the pioneer discoveries, and I found this because this is the kind of person he is. This was a research award that was given at UC San Francisco recently, and here's the same George Gregory writing about this very nice young woman who was a fourth-year medical student, and this was posted on the UC San Francisco website, and it was just lovely to see what he wrote. Rebecca participated in every phase of the study, including development of the protocol, database, and the statistical methods. She did an outstanding job initiating and completing this difficult project in a foreign country. And this was actually a study about different kinds of surgeries for various congenital malformations of the palate. She has the potential to be one of the superstars of medicine in the future. So it's nice to see that people like George Gregory have remained so involved in the transmission of new knowledge. So let's continue our story a little bit about respiratory distress syndrome and why this was so interesting. So in the Vietnam War, again, nobody remembers that but me. In the Vietnam War, there was a new diagnosis that was made, and it was called shock lung. So it was then called shock lung. So the reason it was called shock lung, and why hadn't this entity been seen in other wars, like in World War II or the Korean War? Between the Korean War and the Vietnam War, there was a great deal of improvement in field rehydration of soldiers that got wounded, because they obviously lost a lot of blood and they lost a lot of fluid, and they would die in shock. And then it was discovered that you could take things like, there was lactated Ringer solution or normal saline, and you didn't have to give them blood right away, but if you gave them enough fluid, they could survive the initial blood loss. And you could get them to a hospital. But then, these soldiers that had lost so much fluid and had been exposed to this reduction in fluid for long periods of time, meaning hours, their lungs filled up with fluid and they couldn't breathe. And they called this shock lung because they were in shock. Shock physiologically really has to do with the loss of fluid so severe that your blood pressure goes down and you're unable to perfuse the tissues, something that Dr. Lotipour knows a lot about as an emergency doctor. It was then called Da Nang lung. Da Nang was one of the major cities in the war in Vietnam that those of us who were aware in those days knew about. Here is an x-ray of a soldier with shock lung. So you'll recall from those x-rays that I showed you in the baby, very similar features. This should be nice and bright and clear, indicating air, and you can see it's all cloudy. And so something was happening that was in some ways similar between respiratory distress syndrome of the newborn and shock lung. And again, look at this photomicrograph. Instead of seeing these nice, open, clear air spaces, they're full of fluid and debris and inflammatory cells. So there was something about the lung losing its perfusion that led to this clinical situation. Now, once again, we come back to positive airway pressure. In this case, instead of continuous positive airway pressure, this is positive end expiratory pressure. It's the same theme. And again, look at this figure on top here. Here's your arterial oxygen concentration. Normal is about here. And as you increase this positive pressure, you can see that the oxygenation improves. So the discovery that was made in the early 1970s in newborns about using positive pressure to keep the lung open and promote oxygenation became extremely useful in saving people who had shock lung. Now, we don't now see shock lung as much because in wars, alas, because the rehydration gets taken care of so quickly. But we do see it in trauma. And we do see, and I know that this is something that Shahram and his group are very aware of, is to try to prevent this. But it is interesting that it was the discoveries that were made in newborn babies that ultimately led to a therapy that affected not only babies, but affected adults as well. So let's now switch gears and talk about what has happened here at UCI and across the country as we think of this translational science and what it means. And this has really been a defining moment, not only in our history, but throughout the country. Let's talk about clinical research in general. So this is a picture from the NIH Clinical Center. So the NIH is the National Institutes of Health. It was established right after World War II. And the idea was that we needed in this country a national hospital that would be a research hospital, that would take patients from around the country who had failed treatments in whatever diseases. And that there would be a place in this country where you could send these patients who were perhaps hopeless and nobody knew what was going on with them. And you'd have the best research physicians, nurses, and everybody in one place, and they could try to focus on these patients. And so this hospital, the clinical center at the NIH, which exists to this day, was established in the 1950s. And I'm going to tell you that there's now a move afoot to expand the possibilities for medical students, nursing students, to spend time in Washington at the clinical center. And for those of you who choose careers in healthcare, I would suggest that this is something you might do because it's a really wonderful institution. They've just started a program now that's called Rare and Undiagnosed Diseases, and we're actually sending somebody to the NIH. So it's free of charge if they select your case. And what they do is, again, so this is a child who's 9 years old, who has sort of an autism-like features where he doesn't really relate. He relates to his family. He doesn't read. He doesn't have verbal skills. And you'll look at this kid, and he will become cyanotic in front of you, just like this. He'll turn blue. He's not breath holding. He just turns blue. And we have done everything we can to try to figure out what's going on. It just occurs suddenly, then it goes away. And he has these episodes. None of us can figure it out. We sent him up to Stanford. We sent him to Denver. So we're going to send him to the NIH and see if we can figure this out. And there still are many instances where you've got diseases and conditions that we have no idea what they are. In the 1960s, the NIH created what's called General Clinical Research Centers. And what they were was, these were places in a medical center where you could do research on humans. And the reason this is important is it was described to me, again, with autistic children. So for example, at UCI, UCI has had an interest in autism for many, many years. We just got a large $14 million grant, actually, to create a new center for autism, and it goes back many, many years. When we first created the Clinical Research Center, all of the autism researchers wanted the autistic children to come to our clinic. And the reason was because they were doing the research on these autistic kids in the regular pediatric clinic. Now, autistic children, you know, their behavior is very idiosyncratic. And to draw blood from them was not easy. I mean, they would scream bloody murder. So there you are, if you were trying to do this research in a regular pediatric clinic, and you've got like a waiting room out there, and there's a bunch of kids, and now you've got this autistic kid, and what do the kids hear? They hear a blood-curdling scream coming from behind the door, and then you say, you know, Mrs. Smith, Dr. Cooper is ready to see you. This was not a healthy environment. So, you know, one of the immediate things and the reasons to have these specialized areas was because for some reasons like that, you needed to kind of separate the research from the regular clinical care. The other thing is you can imagine, let's say I was doing a study on asthma, and I wanted to see if a particular drug works. So the experiment would be, I would give, a child would come in, was wheezing with asthma, I would do some kind of a pulmonary function test or a breathing test, and I'd have to do that every 10 minutes because I was really, it was critical for me to know, you know, when, if the drug had an effect, when would I see it, how long would it last? So I've got a nurse, and I'd ask the nurse to do these measurements for me. Now I've got a research patient over here, and then I have someone who comes in off the street who's really sick with asthma. Now I've asked the research nurse to take these measurements every 10 minutes, but I've got this sick patient who really needs a lot of care. What's going to happen to my research? I mean, obviously you've got to take care of the kid of the patient who's really in trouble. You're not going to let this go, well, your heart rate is about 0, but I've got to do this measurement over here because Dr. Cooker asked me to make these measurements every minute. That's not going to work. So there really was a lot of rationale for creating these general clinical research centers that was, the infrastructure of which was supported by the NIH at academic medical centers. It made a lot of sense. So these were created throughout the country in the 1960s. And we became one of these centers back in 2000. Probably not worth going this much. And then Bob Dylan, I'm probably the only person who has ever heard of Bob Dylan. Actually, my daughters know Frank Sinatra. Does anybody know Bob Dylan? So he's still singing, right? I mean, he has this sort of terrible scratchy voice now. He did then too, but we thought it was really cool. You know. So, this was one of his famous songs was "The Times They Are Changing," and the times they are changing now. So here's what happened with these general clinical research centers. They've been around from the 1950s through about 2000, and they were becoming stodgy. They were becoming very insular. They weren't doing the things that Gregory had talked about. They weren't being innovative, and they weren't being, what's the word that Francis Collins used? Disruptive innovation. They weren't really shaking things up. And so this guy, Elias Zerhouni, said, who was the head of the NIH in the early part of the 2000s, said, we've really got to change this whole thing. And here's Zerhouni, and he decided to completely end the GCRCs. And I'll never forget, I think it was 2004 or 5, so I was asked to review a general clinical research center at Martin Luther King Medical Center. How many of you know Martin Luther King Medical Center? So it was Martin Luther King Medical Center. That's also an interesting history. It was established as a result of the Watts riots. How many of you ever heard of the Watts riots? Oh my God, I'm so old. It's only me and you know who remember this thing. 1960s, huge race riots in Watts. 40 or 50 people were killed. And it was decided that one of the problems was that there wasn't sufficient access to healthcare, so this Martin Luther King Drew Medical Center was built in those days. And I was a reviewer for their GCRC, and the people from the NIH, who were the NIH bureaucrats that were told me, by the way, there's going to be no more general clinical research centers. Now, our general clinical research center at that time was about 4 or 5 years old. We were really proud that we got it, and then they said, it's over, buddy. And the NIH created this whole new mechanism, which I'm going to talk about right now, that would be used to support clinical research. Zerhouni developed what he called the roadmap for research, accelerating medical discovery to improve health. So let's talk a little politics at the time. You know the NIH is a federal agency. It's the largest agency in the world that supports biomedical research. But it's political, right? I mean, everything at Washington is political. And so you've got competing interests all the time for the limited amount of dollars that we have in the federal government. And people who were critical of the NIH were saying, you know, it's a great organization, but all you're doing is you're studying fruit flies, and you're studying mice, and you're studying rats. And having grown up with this period, it was true, because the underlying idea was that the way you would enhance biomedical discovery was through understanding fundamental biological mechanisms. So think about what I'm saying. In other words, if I'm interested in cancer, I need to know what controls cell division. I mean, there is certainly a logic in that. I mean, and if I can figure that out, then I can figure out how to cure cancer. Now, the other side of that coin would be to go and say, no, you should kind of build on the information, whether it's anecdotal or otherwise, where people with cancer have gotten better, and start with that and move in that direction. So you've got these really opposing points of view. I mean, it is kind of interesting that let's take two serious conditions in pediatric health. Obesity on the one hand, which you've all heard about, and childhood leukemia, okay? Childhood leukemia is a rare disease. I mean, it's a rare disease. Untreated, childhood leukemia is almost inevitably fatal. If you get childhood leukemia and you don't get treated, you're going to die. Obesity rarely leads to death, but it's so common that the number of obesity-related deaths surpass the number of deaths that are related to childhood leukemia. Now, here's what's really interesting about this. What percentage of childhood leukemia can we cure now?
100.
It's not 100. I wish it were 100. It's about 70 or 80%. It's a very high percentage. all trial and error. We don't know why a lot of these drugs work. The fundamental knowledge, and there's been a lot of discovering sort of why a cell decides to become malignant, we still don't get that. But through the application of sort of good observational research and years of clinical trials, we can cure most childhood leukemia. It's rather remarkable when you think about it. Obesity? We haven't. It's very difficult. And even though, and here's the irony, do we understand why you become obese? Well, sure, physiologically, it's simple, right? I mean, energy intake, energy expenditure. You don't have to be a rocket scientist to know that. But the social, political, environmental, everything else, all these factors, the accessibility to low-cost, high-calorie foods, the advertisements on TV, whatever you want to do, those other things are so compelling that here we've got this epidemic of childhood obesity that is unrelenting. We haven't really put a dent in it yet. So not everything is what it seems. And so when you have the NIH, which in those days was predominantly funding fundamental research, very, very focused research, it was open to the criticism that, yes, all you're doing is you're studying fruit flies and transgenic mice, and you're not really getting at stuff that's going to affect human health. And Zerhouni recognized that, and he said he heard what Congress was saying, and he didn't want the NIH to get zapped politically. And so he said, you know what? We've got to redo this whole thing. We've got to make a revolution. And he was very, very smart, in my opinion, to do this. He wrote an article that I think you guys all should read. Maybe we should add this to the... This came out in 2004 or 5 in the New England Journal, October 13th. Translational Clinical Science, Time for a New Vision. And here's some of the things that he wrote. This is our own Dr. Desai, by the way. It is more and more difficult to recruit, mentor, and retain a critical mass of clinical and translational scientists. Proper training and mentoring of scientists capable of conducting truly innovative, patient-oriented research require dedicated time away from the escalating pressure of clinical service demands. So he recognizes this, and this is very true. The finances of healthcare right now are such that even at an academic medical center, most physicians are not going to have a salary means, to support their research and their teaching activities. Let's go back to one of my first slides, Abe Flexner, right? This is this guy in the 1915 who was sent around and he said, we need to have clinicians, practitioners, juxtaposed, interacting with, in constant communication with scientists. It was a problem then, it's still a problem now. And so part of what Zerhouni wanted to create was this new mechanism of funding where we could support and create a home for people who were at the bedside, but also talking to people who were in the laboratory so that we could speed this process up. And he wrote in this article, it is our intention and hope that this focused and significant commitment to the creation of a new vital and reinforced academic discipline and a home for translational and clinical science will ensure that extraordinary scientific advances of the past decade will be rapidly captured, translated, and disseminated for the benefit of all Americans. I should have a little music, right, when we do that. So he ended the GCRC program. All my colleagues were panicked, and we developed these things called these CTSAs, the Clinical and Translational Science Awards. UCI's story is an interesting one. Deli knows it very well. We never gave up, right, Deli? And then after several tries, we were funded with a $20 million grant in 2010. And now we're starting to worry about our renewal for the next 5 years. So let me just tell you from my own personal experience, having been doing human-based biomedical research really my whole medical career, that one of the things that the CTSAs have done is create an atmosphere of sharing and multidisciplinary team science that I've really never witnessed before. So we have committees now that, for example, in my field in child health, we have a committee that's called the Child Health Oversight Committee. And it's composed of pediatric researchers from all around the country. And some fantastic projects have been emerging from this. So for example, they put together something very simple where if you're an investigator and you want to study a new drug in a relatively rare disease, obviously at a single medical center it's sometimes hard to find enough patients with that disease to be able to do a decent clinical study. So what you've got to do is network with the rest of the country. So through this mechanism, through the CTSAs, there's now, we get posted every couple of weeks, hey, Dr. John Smith from the University of Arkansas is studying a rare clotting disease. He's got an idea. What, do you have patients? And then all of a sudden, everybody kind of gets together and they do their communication, and voila, you've got a study that 10 years ago you would never have been able to do because you wouldn't have had this ability to communicate with other investigators. So this is really rather important. What we're seeing is a real sea change in biomedical research that other researchers have seen already. How many of you read the book Aerosmith by Sinclair Lewis? Did any of you read Babbitt when you were in high school or any of that? I guess this is different. So Sinclair Lewis is a friend of Bob Dylan's and Jack Kennedy. So, so he actually won the Nobel Prize in Literature in the 1920s. And this book, Babbitt, is probably outdated, and if you read it now, you wouldn't like it. And do any of you actually read anymore? So what this is about is in the 1920s, and it's about this young physician, his name is Aerosmith, who has to make this choice in his life. Become a sort of a Park Avenue, you know, in New York, Park Avenue practitioner, makes a lot of money, high society, or be a poor researcher. And you know, spend his days kind of knocking his head against the wall of research institutions. It's remarkably up to date, even though it's from the 1920s. The motif then was, there was a lot, in the 1920s, there was a lot of interest in infectious disease research. I mean, this was the big killer of human beings in the 1920s. It was not heart disease, it was not cancer, it was infectious diseases. We take it for granted that we'll come up with some antibiotic if you should get an infectious disease. That was not the case in the 1920s. Remember, penicillin wasn't even discovered yet, right? So there was a lot of interest, and they were studying bacteriophages. And the guy who helped Sinclair Lewis write this book wrote another book that you probably never heard of called Rats, Lice, the Microbe Hunters. Did any of you ever read that when you were a kid? So it was a history of people like, you know, that were fighting against the microbe. Delhi probably heard of that book, right? That's all. Exactly. So he wrote that book with Sinclair Lewis. So the point is, in this story, at the end, he chooses, of course, he's our hero. He goes off and he decides he's going to give up, you know, the riches of being a lucrative practice, and he's going to go be a researcher. Now, what struck me about that book was, in those days, the concept of his being a researcher is that he and a friend of his had a lab in a log cabin in Vermont. You know, when they had like a microscope and maybe some electricity, that's all you needed. And that image of this sort of iconoclastic, pioneering researcher who will go off and discover a cure for cancer on his own or on her own persists to this day. And the truth of the matter is that I think, except in very, very rare instances, science is going to be a series of incremental changes. And the people who get this are the physicists. So a couple of weeks ago, we have this organization of all of these Clinical Translational Science Awards from the 5 UC campuses. And they like us. And so the representative from the Office of the President is an astrophysicist. And he gave us a lecture. He said, listen, we figured this out. When you look at a paper about, you know, like, what was it, the Higgs boson? Did you guys remember that from a couple of months ago? You know, there's 30 or 40 authors on that paper. When you look at the stuff that's coming out of the Mars Curiosity, you know, those papers are going to have 30 or 40 authors. And what happens is, in the typical academic advancement committee, they're going to look at this and they'll go, 30 authors, you know, you didn't do anything for this project. When in fact, those projects are so complex that every one of those individuals is absolutely critical for the success of that project and made a huge contribution. To discover cure for cancer, to do these modern kind of studies where the complexity of how genes are regulated is so far beyond what we thought with the Watson and Crick model, right? One gene, one protein. We know that that's like nothing. It doesn't describe 1/10 of the complexity. That you're really going to need these teams of people. And so what we're seeing is this sea change now in our own field and a willingness to do team science. I'm going to stop talking soon, right, Jessica?
Whenever you're ready.
Let's see. And we'll end with Francis Collins. Okay, so very political. Zerhouni was the Bush appointee for the head of the NIH is appointed by the President of the United States. So it's fairly political. So the next head under Obama was Francis Collins. Now he's an interesting man. Does anybody know who Francis Collins is? So Francis Collins was the head of the Human Genome Project. The Human Genome Project, your parents' taxpayer money, as a parent I have to give your parents some credit. So this was a multi-billion-dollar project, the goal of which was to sequence the human genome. So have we sequenced the human genome? Yes. How many new therapies have resulted from our sequencing the human genome? Maybe 1 or 2 so far. So Francis Collins is a smart enough guy to say, you know what? It's really cool that we did this, that we sequenced the human genome. It brought about absolutely revolutions in the technology of how we look at these complicated issues. But what he wants the NIH to do now is to build on the revolution that Zerhouni made and figure out a way that we really move this phenomenal knowledge into the translational realm. And I'm going to end with this. So what he did was he created a new center called the National Center for Advancing Translational Sciences, NCATS. And NCATS' mission is, I did that because I study pediatric exercise. This is from the NIH, and I wanted to point out how important exercise is. So just by chance, they put the picture there for me. Let's see. And this is it, and we'll end here. So the mission of NCATS is to catalyze the generation of innovative methods and technologies that will enhance the development, testing, and implementation of diagnostics and therapeutics across a wide range of human diseases and conditions. So you guys are part of this course that is related to this because we are part of NCATS. All these CTSAs we're part of this National Center for Advancing Translational Sciences. You guys in this course are getting this introduction, and you're going to become part of actual research. How exciting is that? How cool is that? At a time when all of these things are changing, and you're sort of at the beginning of this new way of thinking about clinical research and basic scientific discovery. So it's really great, and I'm really proud of all of you, and I'll shut up at this point. Thank you very much. What's next, then?
No, we have time for questions.
Yeah, questions. Don't be shy, really. Come on, you have to ask questions. I don't believe that you're just shy. Come on, you've got to be. Not many of you were asleep. I was very proud of you.
Why did you want to go into research?
Why did I go into research? Okay, so the question is, why did I go into research? It's a really good question. I'm still trying to figure it out. No. So, I went to medical school with the idea of being a practitioner, the way most people who go into medical school do it. The MD degree is not a research degree. We're taught at universities. The first 2 years of medical school are pretty much basic scientists. And Flexner did create this mechanism where all the medical schools, almost all the medical schools are part of universities. But you usually go, and I mean, I was going to, save the world kind of thing. I was going to be a doctor, and I was going to work in areas that had few doctors, and that was sort of my goal. But as you sort of proceed in your career, you inevitably come up with these situations where you're treating a patient and you run out of stuff to do. You just can't help this person anymore because you don't have it. You've given all the chemotherapy. In my case, it's a kid with cystic fibrosis. You use all the antibiotics, and you were stumped. You know what I mean? You just said, that's it, I can't, I'm helpless, you know? And so you sort of think, well, what could I do to move that forward? Could I, as an individual who was taking care of a patient that I could no longer help because I didn't have any more tricks in my bag, because the scientists hadn't discovered them yet, could I contribute to that process? So my own personal journey was I sort of had this crossroad when I finished my pediatric training. I did my medical school at UC San Francisco, then I did pediatrics at NYU Bellevue. I wasn't a patient at Bellevue, but it was a great pediatrics program, and I really had this choice whether I was either going to join the public health service and work out. I haven't told Joe the story because he'll probably never let me forget it. Either I was going to go work in some place that really had very few physicians, or there was a fellowship that had just opened at Columbia University in pediatric lung disease, which I was really interested in. And I remember it was a very, very tough choice about which direction to go in. The person that was my mentor, his name is Bob Mellons, he's still alive, he's in his 80s, he's still doing research at Columbia, said, you know, what you're going to do is I'm going to take you away from the clinic, and I'm going to put you in the lab for 2 years, because I hadn't had a laboratory background. I actually majored in sociology, community studies. I can't tell this stuff. He's going to come back at this. Because I know your secrets, you know. In college, you know, so I didn't really have this lab experience. He said, and what I think it'll do for you, you will become a better physician. In other words, you'll become a better physician because when you sort of go in and see how this knowledge is created, you know, that you use, you'll appreciate it more. And even if you don't become a researcher, you'll understand how to read an article better, you know, because you'll say, you know, this guy said this, but this is ridiculous, I know this could be. And I sort of got hooked. And that's what happened. I had a great time at Columbia. It was really, really interesting. That was just my own particular journey.
So you have a lot of examples to pick from.
Yeah.
So I think it's distinguished research career. I gave the students, and certainly the respiratory distress syndrome is a great example. I also gave them a paper that you wrote with other disciplinary experts on the breath biomarker work, which I thought was a wonderful example of bringing disciplines together to solve. So maybe just a short sentence about how that came about.
Sure. So that's a great question. You have that article I saw. So if you look at I think the authorship on that article, does it include Sherry Rowland? Is he one of the authors?
It's Dr. Blake.
Okay, so I'll give you a little history of that interaction. So as a pediatric researcher who was interested in exercise and pulmonary disease and stuff, one of the things that you discover when you do human research is that you don't have the freedom that you have if you're doing cellular or animal research. And so let me give you you don't mind my stories, they don't mind my stories. So I was on an NIH study section. The way the NIH works is people apply for money. How do you give out the money? Well, it's called peer review. That is, you have groups of scientists and physicians who look at your grant. They can't give everybody the money, and they rank your grant. And I was a member of one of those study sections, and it's a great experience to do that. These study sections in the NIH are about 80% PhDs and about 20% MD. Most of the biomedical research that's done is done by PhDs because the PhD is a research degree. You learn how to do research. The MD is not a research degree. The MD is a clinical degree. And one of the things I learned, which is really relevant to this whole issue, is that I would see that, and this was true for my grants as well as an MD, that we didn't do as well in these rankings as the PhDs did. And I finally figured it out. And you get a grant from an MD, and it'd be, you know, we want to discover the cure for asthma. And it would have 1,000 hypotheses, and it would be all over the place. And then you would get a grant from a PhD, and it's there is a receptor that occurs in 1/100th of the Caucasian population, which under a certain temperature actually causes smooth muscle constriction, and here's why I attack. Okay, so that one would get funded in years from now. I finally figured this out. So those of you who've gone to go to medical school and stuff, you're going to be on rounds, okay? You're going to have a patient, and your attendant, though they can't be as mean now as they used to be in my day. Let's say that this particular patient on his laboratory results has high potassium, hyperkalemia, okay? So in my day, the attending would pick on you and say, Dr. Cooper, what are the causes of hyperkalemia, right? So there's probably, what, 150 causes of hyperkalemia?
But there's only a few that he wants, I'm sure.
Right. So as a medical student, as a physician, you sort of have this concept of assuming responsibility for your patient. That is, you need to know. You know, you can't, it's sort of the opposite of teamwork. It's in the sense that, yes, you trust your other people, but did you really look at the x-ray? I mean, did you go look at it? Did you look at the lab thing? Maybe you missed something. Maybe you missed cause number 102 of hyperkalemia, which is why that patient is unconscious right now. And so you would kind of go through all 102. You know, if you missed something, you were in big trouble because the attending would go, yeah, but you missed Tsutsugamushi disease, right? And that would be something more trouble. So I realized that the NDs were writing grants like that. They were thinking of all the possible reasons that a child could have asthma, and they were writing a grant to kind of get at the whole thing because you want to find the cure, right? The Ph.D. is taught to write a proposal where the result of your experiment will give you a definitive answer. That means you've got to make the question smaller and smaller and smaller to get to the point that you can write a grant over a span of 4 or 5 years at a cost of a couple $100,000 per year, where at the end of the day, I'll have an answer to this. And the reviewers say, yeah, you'll be able to answer that. And they don't, and they ding you. So one of the difficulties in dealing with human research is that you're dealing with the organism that you want to deal with, that is the human being, but the complexity is enormous. I mean, I can't just study one lung in a child. You know, I couldn't do an experiment that said, I'm going to take a healthy child, put a bronchoscope down in a healthy child home, you know, anesthetize, you know, it's not going to go. So we were always looking for minimally invasive ways of getting information. Okay, so there had been this literature about looking at certain gases that you could detect in the human breath. Now, when you think about it, the large concentration gases in the human breath are oxygen, CO2, nitrogen, right? That's the big percentages. But even carbon dioxide, which is just a couple percentage, there's a lot of carbon dioxide there, right? There was this literature about gases that you could detect in much smaller quantities, and a number of folks had written papers about, gee, if there's malvinaldehyde, which is a gas that's produced as a result of oxidative processes, that if you find a lot of malvinaldehyde in a person's breath, that maybe it indicates excessive oxidative, damaging oxidative processes. So we were wondering if we could find someone at UCI who did this kind of work, at least who did this kind of work. Well, UCI had a lab that had been established in the 1980s by Sherry Rowland. Sherry Rowland was a chemist whose emphasis was on atmospheric chemistry and on organic compounds that you could discover in the atmosphere. So remember, the atmosphere is mostly oxygen, CO2, nitrogen, and then argon, a few other gases. And he developed over the years tools that could detect gases in the parts per million, parts per trillion range. And most of the organic compounds that you measure as gases floating around in the atmosphere are biologic in origin, right? Makes sense. So we started thinking about this, and I called Don Blake. Don Blake had been Sherry Rowland's student. Sherry Rowland won the Nobel Prize in 1995. He's the guy who discovered why there was a hole in the ozone layer, if you don't know this. This was a UCI professor. And what he discovered was that I don't know if any of you remember, but the chlorofluorocarbons were eating up the ozone, so much so, because where were these chlorofluorocarbons? Anybody remember? All your sprays, all your hairsprays and shaving cream, and this is where it becomes ironic, asthma medication, if any of you have asthma, those are all chlorofluorocarbons. Put a footnote there because we're going to come back to that. So Sherry Rowland discovered that it was these chlorofluorocarbons that he was able to measure with such precision. Don Blake was running his lab, this is about 8 or 9 years ago, had been a grad student, had gone with him to Stockholm when he received the Nobel Prize, was later to become the chairman of the Department of Chemistry. So we had looked at this literature and it seemed to us, gee, if we could do that here, maybe we could get insights in a minimally invasive way, which would be great for children, into diseases like asthma or cystic fibrosis or even metabolic diseases. And so we started working, and that paper describes, this is the glucose paper, right? Yeah. So in that paper, which was Pietro Delasetti, who was one of our associates, was the head of it, basically what they found was that you could, through the detection of these very, very rare gases, actually figure out what somebody's glucose concentration was from human breath. You know, and that's really pretty spectacular. And it's really in line with this thing right here, which says to catalyze the generation of innovative methods and technologies. I mean, wouldn't that be cool? And so now this idea, Alan Barber of the Department of Microbiology is using this to try to detect potential terrorist gases in tiny, tiny quantities, because most of them are organic. There's a paper out on signature gases of bacteria. You know these gases smell bad. I mean, E. coli, et cetera. By the time your nose can detect them, now our noses are very, very good at this, by the way, but they can't get into the parts per trillion or parts per quadrillion. So this has sort of opened up a whole new field of trying to investigate human disease using these novel techniques. And it's chemists, physicians like myself, mathematicians, statisticians, all sitting together in ways that they might not have before to try to better understand how we could use this as a biomarker. Now here's the irony, and we'll get back to the chlorofluorocarbons in asthma. So when we were doing these studies, we started doing them about 8 or 9 years ago. Because of Sherry's work, chlorofluorocarbons have been banned as aerosolizing agents. Now, so the asthma drugs, it's only in the past 5 years that they're starting to use new, because you still have to aerosolize the medicine, because otherwise its value is that you can just take it as an inhaled agent, breathe it right into your lungs where it helps. So when we started doing these studies with Don and Sherry was still alive, Dr. Rowland died, it was about 8 or 9 months ago, a year ago. We had a guy with asthma come into the lab, and we found really high concentrations in his breath of the aerosolizing gas. And he told us that he was an asthmatic and that he had used his inhaler a week before. Now, one of the big problems clinically that you have, particularly with children, is if a kid comes in wheezing, and the first thing you ask is does the child have asthma? Yes. Has he been taking his medicine? Well, sometimes the parent knows, sometimes he doesn't. You know how kids are. And it's a very important question, because if the child had been taking his medicine and still had an asthma attack, you're going to treat him differently than had he not been taking his medicine. So wouldn't it be cool if with a breath test, we could tell whether or not the kid had been taking his medicine? Because the trace of the aerosolized gas would be the clue to whether or not the child had been taking the medicine. So that's a great idea. The problem is, because of Dr. Rowland, they're now switching all the gases. So we have to start from ground zero and look at how the new generation of aerosolized gases, what their kinetics are within the human body. I think this is really kind of an interesting story. Any other questions, or are we?
Well, we can take a break. I think we're going to go through the article that Dr. Cooper just kind of summarized when we get back.
So, any other questions before we break?
So you have both some med students here, you have master's students here, Dr. Cooper, and also our PH 194 students.
Fantastic. Thank you, guys.